In this presentation, we will present our work on advancing text-driven chest X-ray generation with policy-based reinforcement learning. Diffusion probabilistic models have significantly transformed the field of conditional image synthesis, particularly in medical imaging across various image domains, by facilitating text-driven image generation. However, it remains challenging to express complex diagnostic differences, such as minor tissue texture variations per patient or disease. This problem occurs because the model relies on estimating the log likelihood of the training data, which leads it to mainly produce images that mirror the training data's distribution, thereby failing to accurately represent minor variations characteristic of medical images. Meanwhile, recent studies in computer vision propose observing diffusion denoising as a multi-step decision process, facilitating the application of policy gradient reinforcement learning methods as seen in the video. Motivated by such potential, we introduce CXRL to integrate policy-based reinforcement learning into text-to-medical image generation, specifically focusing on chest X-rays. Existing methods fine-tunes image generator with policy-based RL to represent broader image expressions. Thus, we first integrate policy-based RL into medical image synthesis, by tuning an image generator to enhance text-to-medical image generation using non-differentiable reward functions. However, our empirical observations indicated that solely optimizing the image generator limits the scope of pathological expressions. Consequently, we introduce CXRL, which jointly fine-tunes the image generator and learnable adaptive condition embeddings to condition the image generation process flexibly, broadening the range of pathological features represented. Prior research has integrated human feedback into RL for general image generation, but applying this to medical imaging faces significant hurdles due to the medical field's complexity, making quantitative assessment challenging. However, in such complex scenarios, Musweiler and Poston highlight humans' ability to make more consistent and accurate judgments through relative comparison, suggesting a potential path forward for medical image evaluation. Therefore, we adopt the RLCF approach, employing human-like comparative evaluations to improve medical image synthesis. RLCF rewards images that surpass an anchor model's quality and penalizes inferior ones, promoting higher quality image generation. We address three main challenges in generating report conditioned CXRs with targeted feedback to achieve our objective. Our approach incorporates three distinct feedback mechanisms for goal-oriented CXR creation. At first, generated CXRs often face scaling issues, obscuring essential details. To counter these, we introduce a posture alignment reward which quantifies the magnitude of transformation obtained from the frozen posture alignment model. It aligns CXRs to the canonical pose, enhancing posture precision and visibility of essential regions. Next, we improve the pathological accuracy of generated CXR by integrating the RLCF to enhance feedback reliability. Our diagnostic condition feedback compares the classification accuracy scores from our model's CXR against those from an anchor model, XHAT. Finally, we enforce the generated CXRs to better align with their reports. To address this, we use RLCF to measure the similarity score differences between our model's generated CXR and report, and the anchor model's CXR with the same report. Integrating the introduced reward feedbacks, we update the policy gradient in a RL manner, by interpreting the diffusion denoising process as a series of actions, aiming to maximize a reward function that evaluates the adherence of generated CXR to a given report. This process is formulated by an objective function that targets the cumulative reward across the diffusion trajectory. This is a qualitative comparison between previous state-of-art reports to CXR generation models and ours. The blue and green texts match their corresponding colored arrows. First, look at red circle. It represents disagreement against input report or artifacts. Our CXRL exhibits superior agreement between CXR and report compared to the baselines, especially in their capability to avoid generating unmentioned objects. RentGen detects a pacemaker contrary to the report content while CXRL maintains semantic consistency with the report content by ignoring pacemaker. In case B, RentGen generates sternal wires that are not mentioned in the report, whereas CXRL does not. In terms of diagnosing specific conditions, CXRL shows a high level of agreement. For example, while LLM CXR and RentGen either fail to identify or incorrectly generate hilar enlargement with artifacts, CXRL accurately represents them. Second, look at the yellow boxes. It represents misaligned posture structures or missing crucial areas. While others occasionally miss some details, our CXRL consistently shows the clavicle and costophrenic angle in their entirety. In contrast, RentGen often loses parts of critical areas due to inadequate posture alignment. This table shows the evaluation of our generated CXR across 3 metrics, reflecting the rewards we targeted, which is a key quality of CXR. Our experimental result confirms our rewards are enhancing text to CXR generation model, towards the goal-oriented result. This table details the fidelity of our generated CXRs, using the FID and SSIM metrics for benchmarking against baselines. Our CXRL outperforms baseline models, showcasing superior image realism. Thank you for listening.